All right, yes. Hi, I'm Daniel. We wrote the J-code breaking and partially fixing only router with fragmentation. This is work I did together with Christoph and Thorsten. So sometimes Alice wants to communicate anonymously with someone. For example, if she is a whistleblower and she wants to contact a potential journalist. And one way to do so is to use the mixed network circle, which is a system in which a message is routed across a series of intermediate nodes, and each node shuffles all the messages before forwarding them, thereby hiding the path. Now the problem here is that in a mixed network, messages usually have to have the same length, because otherwise they would be re-identifiable by their size. But sometimes Alice wants to send a larger message, for example, a document or a video. And one approach to solve this is to use some sort of fragmentation, where Alice simply splits her message into multiple smaller parts, and then she sends each of the smaller parts through the mixed network to Bob, and Bob can reassemble the message once he received all of the fragments. Now, the issue here is that Bob could be malicious. And if Bob is malicious and suspects that Alice is the one talking to him, then he can try to cause some packages for Alice. And this will cause a noticeable signal because he will start receiving partial documents, like documents where parts of them are missing. And this allows him to confirm Alice as the sender. But this is not entirely new, this approach. Already in Maxminian, George et al. Have talked about multiple message tagging attacks. They have left it for future work though. And Kuhn et al. Have talked about the dropping bound and their SOK on performance bounds in anonymous communication systems. But what we wanted to know is, does this attack work in practice? And if so, then how can we potentially prevent it? And to understand this, we took a look at NUM. NUM is a commercially available mixed network. And the nice part about NUM is that it has fragmentation built in. So it transparently fragments the messages that are too large to fit into one packet. And additionally, NUM has a mechanism to ensure reliable transport by using acknowledgements and retransmissions, similar to how TCP works. So what we did is we built a small testbed using the Shadow network simulator and slightly modified NUM binaries. And we set up a scenario where we have 3 senders and 1 recipient, and one of the senders is affected by packet loss. And we took a look at Bob's side of the system to see how he perceives the packet loss that Alice experiences. And more specifically, we looked at the time between Bob receiving the first fragment of a message and Bob completing the fragment set that makes up the complete message. And if we look at the results, we can see that for the unaffected clients, this time is very constant. But for Alice, if we induce more and more packet loss, the time to complete the message increases because Bob has to wait for the dropped fragments to be retransmitted before he can complete the message. Now, from this, we derive 3 conditions for this attack to be possible. The first one is that the adversary must be able to drop packets while they can still be linked back to Alice. And in a mixed network, that usually works because the malicious first node can drop malicious packets. The second condition is that the recipient must be able to detect that the packet is missing. Again, this works because usually there's some sort of explicit identifiers, and even if not, you will notice if half of the image or half of the video is missing. And the third condition is that from the subset of packets that are not dropped, we need to be able to derive the final recipient, and this works because each fragment is addressed individually to Bob. Now, in order to mitigate this, what we want to do is we want to break the third condition for this attack. So we want to hide the recipient if not all fragments have arrived. And we do so by introducing a new packet format, where instead of fragmenting the message and then sending each fragment individually, we instead take the whole message and the recipient, and then we put it through an all or nothing transform. And this all or nothing transform is a cryptographic primitive that ensures that you have to collect all of the output before you can undo it. And now that all the fragments have been transformed, Alice can route each of these transformed fragments for the next network so that they meet at the same final hop. And only when all the fragments have arrived here, the node can undo the transformation, learn the recipient and the message, and pass the message on to Bob. Now, there's still a problem because we have these retransmissions. So even if we drop some of Alice's fragments, they will be retransmitted, and the node can collect all of the fragments. And we see this pattern that we saw earlier, where the completion time for Alice is higher than for clients that have no fragments. So in addition to this all or nothing transform, we say that we need to treat the message as the thing that we acknowledge instead of the single fragment. So if Bob doesn't acknowledge the message as a whole, then Alice will retransmit all fragments under a fresh identifier. Now, of course, this brings a bit of a downside, because if we have fragment acknowledgements, then at some point the node will collect one copy of each fragment. If the fragment gets lost, it will be retransmitted, and at some point all of the fragments can be collected. However, if we do this per message thing, then we need like one lucky attempt where all the fragments survive and arrive in one shot. And this is, of course, much more unlikely. So what we expect is that the latency to send a message increases. And this is what we evaluated in the paper as well. And we can see that if we look at the time it takes for the message to arrive, for increasing packet loss, this per message acknowledgement strategy is way worse than the per fragment message, the per fragment acknowledgement strategy. However, for small packet losses, which is what we would expect in reality if you're not under attack, it is still okay. On the other hand, however, if we look at the time it takes, or the time that Bob can measure between the first fragment of a message and the last one, we can see that this per message retransmission strategy removes all the variation, even for high packet loss, which is exactly the thing that we want to hide in order to not give Bob the signal of Alice being under attack. Now, this was the latency. We also evaluated the computational overhead of this new cryptographic building block that we're using, and the packet size. However, due to time constraints, I will not go into detail now, and you can find the results in the paper or discuss them at the post. So, to conclude, we can say that yes, this attack works in practice. However, we provide ways to mitigate it by introducing a new packet format and by changing the retransmission strategy. We have to say that this is a bit of a simplified model, because we assume that the adversary can only drop packets. So if the adversary can delay packets, we again run into issues. So we need to combine this with other mitigations that help against packet delays. And finally, we argue that we need to view mixed-net security holistically, because if we treat it as some sort of opaque anonymization layer, and then we stack other features on top, like fragmentation, we might introduce side channels that help the adversary in de-anonymizing Alice and Bob. If you want to take a look at the paper, please look QR code here, and thank you all for your attention.